of our output machine, it tells us that the weight of both objects, even if they have different masses, are identical. So it's something to think about. When we think about weight, remember, we already made the connection that the tension in a string is a perfectly reasonable and valid way to measure the weight of an object. So I'm going to do something a little more extreme. I'm going to put a much heavier. So right now, there are 20 more grams on the left-hand side for you guys than on the right-hand side. Even though there are 20 more grams here, the weight of both sides of this output machine are identical. And of course, as we expect, it's going to rotate, and the heavier side is going to move down while the lighter side moves up. But the weight is identical because the tension is the same. Because weight is measured by tension. So let's figure out, our question is, what is the acceleration and what is the tension in the string? So to do this, we've got two sides of our output machine. We've got our left-hand side and our right-hand side. That's good. That's going to give us, by using Newton's laws, two equations, and we have two unknowns. Let's first look at the left-hand side. So on the left-hand side, let's define the positive direction to be upward. So one thing I should say, for the rest of this calculation, for now, just so we can imagine it, let's imagine that m1 is less than m2. So in that case, it's going to turn in such a way that m2 goes down, m1 goes up. So in analyzing the motion of the left-hand side, let's say positive is upwards. So we can use Newton's second law. The tension in the string is pointing upwards. The force of gravity is pulling downwards. And that is giving us an acceleration of mass m2. Sorry, left-hand side is m1. So we can solve for the tension. Tension is going to be m1 times a plus g. We've seen that before. This, on the side, left-hand side, m1 is being accelerated upwards against the direction of the force of gravity, which means it gains weight. It's exactly what we were seeing before. So let's call these two equations equation 1. We've got equations on the right-hand side. So in this case, so we don't have to worry about signs of the acceleration. If m1 is less than m2, we know that m2 is going to be accelerated downwards. Let's define that to be our positive direction when we write down this equation. So in that case, the force of gravity on m2 is positive minus the tension, which is pulling upwards, and that's going to equal m2 times g. Oh, sorry, times a. So we can solve for the tension here, and what we find is that we have a tension which is m2g minus a. Again, identical to what we saw before, and that's good, because mass m2, if it's heavier, if not heavier, I shouldn't use that word, more massive, because they are not heavier. They are exactly the same weight. Heavy refers to the weight. If it's more massive, then we know that the output machine is going to be moving, so that m2 is moving downward. That corresponds to what we saw before, and its weight is going to be less. So I've got two equations with two unknowns, and I can now solve for those two unknowns. And I'm going to write down the solution. It's something that you can easily verify with some algebra. The acceleration is m1 minus m2 times m1 plus m2 times g. And the tension is 2 m1 m2 divided by m1 plus m2 g. So first, let's make sure that the units work out properly. The acceleration has a term on the top which is of units mass. The bottom, the denominator, has units of mass, those cancel, and g has units of acceleration. That's good. Tension should have units of mass times acceleration because tension is a force. And that's, again, what we see. Let's turn these equations from just being dumb equations into the physics that they encode for. Let's actually look at some of the limits that are interesting. So first of all, let's look at the case where the masses are identical, where m1 is equal to m2. I should point out, even though in order to discuss what was happening here, I made an assumption that m1 is less than m2, the equations I wrote down, there's nothing about those equations which make that assumption. These equations apply for any values of m1 and m2 that I choose. So when m1 is equal to m2, we can see that the acceleration is 0. That's good. That's what we see here in front of us. That's what we would expect because the force of gravity on either side balances out. What's the tension? Well, remember, the tension measures the weight. And if m1 is equal to m2, what we find is the tension. So let's just say this is m, is just mg. That's also really good because we know that when an object's not accelerating, it should have its normal weight. Its weight that you would get by just placing it on a scale or hanging it from a wire with a force meter and not accelerating it at all. So that's one limit that we can look at. Another one that we can look at, let me just make sure I write down the right thing. So let's look at the limit that we were considering before, that m1 is less than m2. So the normal weight, when m1 is less than m2, if we took the normal weight of either of these objects, we'd say the weight of m1 is less than the weight of m2, but we've now seen that in the output machine they actually have exactly the same weight. That tells us that the weight of m2 must have decreased, and the weight of m1 must have increased. Another way of saying that is that the tension, let me put it mg, so it's the right units. Another way of saying that is the tension lies between the normal weights of m1 and m2. m2 became a little lighter, m1 became a little heavier. So let me put in some numbers. Let's say that m1 is equal to 1.1 kilograms, and m2 is equal to 1.25 kilograms. And remember, g is 10 meters per second squared. That's all I need. That's everything I need to figure out what the acceleration and tension in this output machine is. So we can combine these, and what we find is that the tension is 1.17 times the acceleration due to gravity. So I should specify this, 1.17 kilograms times the acceleration due to gravity. This is not grams, this is acceleration. This is what we expected. The tension is a little bit more than g times the mass of m1. So 1.1 compared to 1.7. m2 has a weight, a normal weight, m2 times g, which is a bit larger than the tension. So again, these equations are bearing out the intuition that we built about what this output machine is able to do. So the output machine is a very good thing to think about when you want to understand the difference between mass and weight. And remembering that we had to make some assumptions about the mass of the string and the fact that the pulley is frictionless in order to write down these equations. Those assumptions, again, in my mind, those are as important. Understanding why those work are as important as understanding the result here and having an idea of how to do the algebra. That's not important really at all. Are there any questions? Okay, I want to do two more things, and one of them may be dangerous to me. what happens when we walk? I don't know if anybody, I personally have not thought about this question very much, and it turns out that at this stage where we just learned about Newton's laws, walking can become an unbelievably interesting thing to think about. So I'm going to hop up onto this. Okay, I think it can take my weight. So let me hop up. There we go. Okay, so I'm the demo now, and I want to show you what it's like to walk. There are two different things that happen when you walk. Kind of cool, it's like on the Jumbotron. Okay, so two different things. There's one foot that remains planted on the ground, and the other foot swings, right? So I'm just going to walk normally first. So walking normally, and then I'm going to do it again and slow down. We're going to focus just on my foot, which is not moving. So when I first plant my foot, I put my heel down. What's interesting is I'm using the fact that there's friction between my heel and the table to slow up that foot. So again, don't pay attention to the other one yet. Now in the middle, my foot is completely planted, and by the time I get to the other side, I'm now using friction in the other sense in order to launch off of that foot. So let's look at that somewhat qualitatively, and then we're going to get to the other aspect of walking, which is the other foot, which is swinging. So let me draw a picture of what your foot looks like, the planted foot, as you go through a step. So this is my model, my interpretation of what your foot looks like as you go through one step. So here's the floor, or the table, as the case may be. And at first you step down and your heel is hitting the ground. So this is one. Now remember, this is the stationary foot. So these three steps I'm showing you are going to be at three different moments in time. At moment 2, your foot is firmly planted. And at moment 3, you're stepping off to move that foot forward. So let me draw the forces that are acting on your foot during that process. At every point here, because your foot is touching the ground, there's a normal force that's pushing upwards. So the normal force is pointing upwards at point 1. But more importantly, you're stopping yourself. You're using friction. So friction is pushing you back. So this is your normal force. This is your friction force. When you place your foot firmly on the ground, at that point you have no friction because you're just pushing on the ground and you just have a normal force that's pushing you upwards. On the other side of this, you have a small normal force still pushing you upwards, but now you have a friction force that's pushing you forward. So this process of putting your foot down, having it be flat, and then pushing it forward is using both the normal force and the frictional force between your foot and the ground. Has anyone here actually walked on ice or tried to walk on ice? Right? Okay. So you guys haven't lived in like Southern California your entire life. I guess you can go to the mountains sometimes. Okay. So if you've ever walked on ice, you might remember that you have to make really, really little steps. To understand why that is, you need to know a little bit more about torque. But you can see that in walking, your frictional force is very important. There's a frictional force stopping you from moving forward, and there's a frictional force that's pulling you, pushing you to move forward once you've gone through the entire step. Let me show you a plot of what the force looks like as you go through an entire step. And this actually turns out to be a very large field of science and of medicine, because and just even articulating, quantifying the forces that are involved is really difficult. So on the top plot, we have the normal force, and this is the stages of the foot that I tried to draw over there. So the normal force is increasing when you're putting your ball on the ground. When your foot is flat, it's greatest, then it starts to decrease when you lift off again, and then finally it's 0 when your foot lifts off. At the other side of this, the frictional forces are acting. So when your foot has 0 normal force, then you have a frictional force that's pushing you forward. Or sorry, the frictional force is pushing forward, it's stopping you from moving forward, and vice versa. So this is just a really awesome, and you can actually go ahead and measure the forces that are involved. And the reason I bring this up is that you can start to actually think about all of the insane mechanics, the physics that's going on inside of your foot as you take a step. There's your Achilles tendon that's pulling up on your ankle. There's your tibia, which is supporting most of your weight. And then, of course, there are all the other bones that are transmitting forces from the ball of your foot back up to your ankle. So the last part of this is an estimate for how fast you need to swing your foot, the other part of walking. So one part is the planted foot, but while you're planting that foot, you're swinging the other one. So you're actually causing a force. You're having to force your foot from one side to the other. It turns out that that motion is very similar to a pendulum. So that's your swinging foot there, and the point, the fulcrum, where your pendulum is attached, is typically your knee. It turns out, and we'll do the estimate fairly quickly, it turns out that the amount of force that you need to exert to swing your foot is 3 times the gravitational acceleration, times each kilogram. So if your foot weighs 2.5 kilograms plus a boot, let's say you have a foot with a boot attached to it. Let me see if my numbers are correct. That's right. So if you have the normal size of a hiking boot, for instance, plus the size of the normal foot, the weight of the normal foot, you have to exert a force which is 3 times that weight. So that would be about 16 pounds to swing your foot from one side to the other. This is why if you've ever gone hiking, or if you've ever gone and tried to find some fancy hiking boot, you try to find the boot that has the lowest mass. Because your legs are going to get very tired swinging back and forth as you're walking along your hike. So let me quickly estimate that for you. So we have to put some numbers into this. So the numbers that we're going to use is that each stride, each step that you take is about 1 meter. So here's our foot, and it's swinging from one side to the other, and the distance that it swings is 1 meter. The amount of time it takes for your foot to do that swing is 1/2 of a second. This is enough information for you to calculate the average velocity. So the average velocity is just the change in distance divided by the change in time. This is 1 meter divided by 1/2 a second, which is 2 meters per second. So if I make a plot of what your foot is doing as it's swinging from one side to the other, it's starting off with 0 velocity, it's going up to some maximum, and then it's coming back down to 0. So it looks something like that, where this is 1/2 of a second, and the maximum occurs at 1/4 of a second. This is your maximum foot velocity, and this is the average velocity of your foot. So these are all quantities that we know about. The maximum velocity of your foot is greater than your average, and it turns out that it's a good approximation that your maximum velocity is twice the average velocity. So that gives you a maximum velocity of 4 meters per second. Now to get your foot going from rest up to this point of Vmax, you have to accelerate your foot. So let me draw what the acceleration looks like. Here the acceleration is positive, here it's 0 because the slope is 0, and here it's negative. So that's your acceleration. And you can calculate the average acceleration between the moment that you start moving your foot and halfway through its swing. So here you have delta V over delta T. In this case, you're going from 0 to Vmax. So you have 4 meters per second, and you do that in a quarter of a second. So you get 16 meters per second squared for your average acceleration as you go from the maximum to 0. But just like the maximum relationship between the maximum velocity and the average velocity, that has to get multiplied by 2 to get the maximum acceleration, which is 32 meters per second squared. So since you're taking your foot and you're accelerating it, the maximum acceleration is 32 meters per second squared. If your foot weighed 1 kilogram, or if you were trying to accelerate 1 kilogram with this maximum acceleration, that means that the maximum force is going to be 1 kilogram times 32 meters per second squared. Since the acceleration is about 3 times the acceleration due to gravity, that means that the force that you'll need to move an object is going to be 3 times its weight, its normal weight. This is going back to our discussion of weight versus mass. This is giving you the weight. So again, it's pretty amazing. The normal average boot weight plus the weight of the human foot, you have to exert a force that would be equivalent to lifting 16 pounds in order to swing your foot from one side of its swing to the other. So using these ideas of forces and understanding how walking occurs, it not only helps you understand what's going on in terms of physiology, but it can also tell you something about why you get tired on a long walk with heavy boots. So have a great weekend.